Okay, we'll continue with our discussion of software development. And see, here's now about testing. First of all, testing is huge. Usually, once you write your program, when I say testing, you don't just run it once and try one value and say, oh, good, it works, and then publish it and sell it. You're a fool if you do that. You test it thoroughly, okay? And so the point here is choosing appropriate test data. Now, we'll talk about this example in a second. First of all, this kind of situation happens all the time. Most people's electrical bills like this. Like the first 400 kilowatt hours you use, you charge one rate, and then like the next 400, you charge a different rate, and then everything after that's a third rate. It's a typical structure. So think about what I just said. What are the breakout points then? 0, 400, 800. And you want to test those values, the breakout points, and then also anything in between. You want to check your code on a negative, which isn't valid. You want to check your code, see what it does. You want to check on something, anything between 0 and 400, anything between 400 and 800, and then some value is bigger than 800. Now, by the way, when I say you check your code for a negative, what should it do in case of a negative? It should respond that that's not appropriate. Like if the person's typing in a number of kilowatt hours they use and they're typing a negative, you should say, well, try again. Type in something that's non-negative. It should not, a robust program should not just ignore it. It shouldn't produce an answer for that, but that was not an appropriate input. It also should not crash. See what I'm saying? So when I say test it, I don't mean that it'll automatically like return an answer for all of these. It should behave appropriately for all of these. Now, if you look at this, what are the cutoff points? 10 and 25, and 0. Because once again, the weight can't be negative. So 0, 10, 25, you want to test those breakout points. And then once again, you pick some number from some number is less than 0, some number, any number between 0 and 10. And from each interval. And that's your test data. Okay? Now one thing I want you to understand is when I got this problem, it's an old AP problem, and I took something out. It said, in the original, it said that the precondition was that the weight would not be negative. It was a non-negative weight. In which case, you didn't need this test for the negative. In fact, you shouldn't have. You wouldn't choose that extra choice. And so be careful. Same thing's going to happen when you do the code writing on the AP test. Some of the times when you're supposed to write a method, one of the preconditions is the input will be non-negative. You're guaranteed that. In which case, you don't have to write code to deal with that problem, right? If they don't say that, though, you do need to be careful about it. Make sure your code behaves correctly if they're given negative and negative is inappropriate. So that's the basic idea there. Let me say again, a big deal these days is called test-driven development, where the person, they write the test first. And when I say write test, they're saying, for this input, we expect this output. And a good example is, if your program is supposed to find the area of something, well, you know the formula. You do the math yourself. You say, okay, for an input of 3, the output should be this. And you know the output should be. You set those tests before you write any code. Then you write your code to max those tests. And doing that makes it so you're much more likely to be on the right track, to write the right kind of program that's doing what it's supposed to be doing. And so we write our code and then test it backwards. But that test-driven development is a new thing. Now, I'm going to give you this PowerPoint. Actually, it's out there, as you know. In the PowerPoints folder, I put a new folder at the very beginning, actually. So you want to go and look at this. Some of these things we talked about before, like the types of errors, I'm not going to go through. Let me skip ahead. Now, when we talk about object-oriented design, I'm just going through some of the basics here. You start by identifying classes, and basically you look at the nouns in your problem that you're trying to solve, and the big nouns, not every little tiny noun, but those basically become your classes. Then you want to figure out what behaviors are trying to happen, and those would be methods. And methods need to be housed inside of a class. And so part of the design process is figure out, your classes and methods, but also which class the method belongs in. And sometimes it's just obvious, sometimes you have options. And that's a design decision. And then when it says relationship between classes, there's 2 basic types of relationships. Inheritance, which we talked about, and then composition, which we've done, but I haven't used the term all the time. Composition is like it has a relationship. Basically, like a car has a lot of components, right? Car is motive, most of wheels, engine, suspension, chassis, doors, all those things. A car is not an engine. A car has an engine. So composition is that. We've written plenty of labs where the instance variable is like a string, so that object has a string, and whatever other instance variables. Now, when it says write the interface, you go and put all the methods in there, or like at this point we're still designing. You're not writing the code. You're just listing the methods. You agree. Your whole team agrees. These are the methods we need in this class. These are the methods we need in this class. You know, and you give it the method signature with the parameters, the return type. And then once again, this team can work on this class, this team can work on this class, and they can write code over here to call the method over here, because they know what's going to be called. They know what it's supposed to do, even though it hasn't been written yet. Okay, and then finally you actually start implementing all this stuff. So that's a typical flow of object-oriented programming when you're designing it. Now, let me skip ahead. It explains more of that, more of the details for you. Here, this is what you know. You don't have to even know that name, but you have to interpret this kind of diagram. Tell me, how many subclasses do you see? Or actually, no, name a subclass. Not player, not scorecard. I didn't hear the other. Good player is a subclass of player, and one more subclass. Bad player. And so the arrows leading up from good player means a good player is a player. That's inheritance. Okay? And by the way, player is not a subclass of comparable because comparable is interface. A player is comparable because it implements interface. Okay, so up arrow means up arrows are and is a relationship. Or is not. It's not a word. Up arrows are represent and is a relationship. Okay. Now down arrows has a relationship. They're composition. So a player has a scorecard. And so if you look at the player class, it would have an instance variable of type scorecard. And so every player has a scorecard. A bad player, so like I said, that's composition. And right here, a bad player is composed of several things. One thing, it will have a scorecard. It'll also have a tutor. Okay? And so basically, whatever you see here, you'll see instance variables listed in that class if it's composed of those things. Okay? And so that's the basics that you have to be able to do to read like diagrams. Listen, if I go back to that list of things you do, remember you figure out what your classes can be, you figure out the relationship between classes. That's this. You draw something like this to lay out, okay, this would be inheritance relationship, this would be competition relationship. You lay that out, and then you start figuring out where your methods go. And you put methods in all your classes, and then you actually start writing code. Okay? Now, top down versus bottom up. We actually talked about that already. I'm actually going to stop here.